Hello, welcome to the next session of the course Mobile Robotics. Today we are going to learn about how to avoid obstacles and navigate in an environment without collisions. Let's start with an example. We have a rectangular environment with some obstacles in the middle. Those obstacles generate holes in the configuration space. So we said that our configuration space was represented by big theta, but now it will be composed of two parts. The part in the configuration space that is free and the union with the part of the configuration space where there are obstacles. Okay, so this subset of the configuration space will create holes in our configuration space, so it will make it difficult for the robot to go from uh, a point in the configuration space to a goal. Okay, so we have that our point in the configuration space now belongs to free, and we want to keep it there. This is our robot in the free configuration space, and the obstacles is just another point, but it belongs to the subset of the obstacles in the configuration space. Now our goal is to find the way to go from Q from any Q to the Q of the goal. For example, in this case, we want to find a path that goes through here and takes us to the goal. There are many ways to do this. There are many ways to achieve this by planning and reactive methods. And today we are going to study a reactive method that can achieve this goal. Our method is called virtual potential fields. It is called virtual because it is inspired in nature, what we have as potential energy fields. And let's give an example. We have like two charges, electrical charges, and if they have different polarity, they will attract. But if they have the same polarity, they will repel. Okay, so we want to use the same idea in the robotic scenario. For that, we will say that our robot, it's a positive charge, our goal is a negative charge, and the obstacles are positive charges. So robot with obstacles will repel, so the robot will try to navigate avoiding the obstacles, and it will try to pursue the goal. Another analogy with the nature and the mobile robots will be using gravitational potential energy. So the robot will be represented by an sphere that wants to go downhill in a valley. The obstacles will be represented as small hills that will try to prevent the robot to go downhill. In this case, our robot is the initial location of the robot is here, and it will try to a desired location around here. This is the simulation of how this will go. It will try to go through that big obstacles, slow down, and go around the obstacles, and finally reach the destination. Now let's start to model this phenomenon using the equations of the potential fields. We get them from physics, and we have, let's start with one dimension when we have a positive charge and a negative charge, and they are being attracted. The equation of the potential field is a function that is proportional to the distance. When the robot or the charge is far, the potential should be higher. If we want to make that function smooth, we can just write a quadratic expression based on the distance. Since this is a one-dimensional case, we only need to subtract the difference between xd, which is the goal, and the x of the robot, and we will square that. In that case, what we will have, if we want to plot that, we will have something like this, where we plot x and the x versus the potential field, and our desired location will be here. The result of the equation of the potential field will be a parabola that passes through the desired point, the goal that where we want to go. The important part here is that anytime and in any position where we place the robot, or if we see it as a ball again, it will try to go downhill. So the force here, the force that will attract the robot to the goal will be equals to the derivative with respect to x, in this case, of the potential field, but it will be negative because the function is growing, the potential field is growing in this way, but we want to go downhill, we want to approach the valley, so that's why we have a negative in front of the derivative of the potential field. And if we compute the derivative of the expression above, we will have that the result is k minus of x minus xd, right? The term k is just a constant that will represent the strength of the potential field. Now let's study the 2D case, which is just a generalization of the 1D case, where we have a point Q that is represented by its x and y coordinates, and we have the two charges, right? The point of this charge is Q. So we want to study the potential field to the goal. That depends on where the point Q is. And similar to the other, to the 1D case, we have a quadratic expression, but now we can write it in a vector form, where K is now a matrix, and we will multiply the difference of these vectors. Right? This is Kg, and this is the vector that we are interested in. So this is the equation, a quadratic equation of the quadratic equation of a ball, where the gain or the constant that will determine the rate or the shape of the ball will be equals to just a diagonal matrix based on some constants, where kx is just the kx that we had in the one-dimensional case. If we want to know what's the force that the attraction force of the robot to the goal, we just need to compute the same as before, that is the force of the goal. But instead the derivatives, since now we are in a higher dimension, we need to use the gradient. We move in the opposite of the gradient. Another way to write down this, or a different notation, is just the partial derivatives of the potential field with respect to the vector q, which is simply equals to k times the the position of the goal minus the position of the robot. And this is the good part. This is the most important expression that we will need to study for the robot being attracted to a goal. Now let's study repulsive forces with the obstacles. So we have the same case in the plane, and we have a positive charge that represents our obstacles that we will denote by QB, and our robot that will be Q, and it can be placed in anywhere. So now, since they are charges with the same polarity, there will be a force, a repulsive force that pushes the robot out of them. In this case, our potential function with respect to the obstacle will depend on the position of the robot and the distance between the robot and the obstacles, but in this case it will be the inverse of the distance between the position of the robot and the obstacle. If the robot is close, the force should be very large, and if the robot starts to be farther, that force should go down and down. Okay, so if we are very close to an obstacle, we want a very high force that pushes us out of the obstacle. Okay, so we can compute the force of that potential, which is equals again to the gradient of the potential of the obstacles minus the gradient. Oh, here it is, minus the gradient, and the result of computing that derivative will be equals to a constant k, the cube of the distance, and we also need to that force has a direction, and the direction will be the gradient of that distance. Now we need to study the total potential. Like, we will take into account the goal and the obstacles. So for that, we will have that for any position in the space, we will have that the potential function will be equals to the goal, the potential of the goal, and if we see here, this will be a ball, right? That will generate a ball, and for any position we will try to drive the robot down to that ball. But if we introduce the obstacles, we also need to add the obstacles to the equation. So we will add the potential that every obstacle generates. For example, here we add an obstacle, and that will be like the small hill that will prevent the robot to go downhill. And if we add more obstacles, it will look like this. Now let's study the total force. We have the equation of the potential, and if we compute the negative of the gradient, we will have that the forces will be similar to the potential, because it will be just adding the force of the goal plus the force of the obstacles. The result will be a vector field where we want to go to a goal. The goal will be here. And for any position of the robot, it will try to navigate through that goal. Let's drive a holonomic robot um, through that vector field, and the solution is quite simple. For our holonomic robot, we know that we can control the velocities in x and y, and that will be our control input. And if we do that, if we make the control input to be equals to the force, the total force of the potential field, we will get as a result we will get a robot that moves towards the goal. And this is an example. This is our robot, this is our initial Q, and the goal is here. So if we simulate for many time steps, we will have something, a trajectory like this. We can see how the robot tried to avoid the obstacles, and in this case it is slowed down because the magnitude of the force is very low, but still the direction makes the robot go through the obstacles and finally reach the goal. We can do that for multiple initial positions, and that's why this is a very robust method. For any position where we are, we just compute the total force and we follow the total force. This is the example for 3 different paths. The method seems very nice, and actually it's pretty simple, but it has a downside. And the main problem here is that we can fall in local minima. In some cases, we will fall into a point where the robot cannot move forward towards the goal. If we see in this example in one dimension, it will be something like this. This is the potential, and the function of the potential will have this shape, where our goal will be here. If the robot starts here, the initial Q will be here, it will go down without any problem. But if the robot starts here, it will fall into a local minima, and this will prevent the robot to go towards the goal. That's the main limitation of this method. Okay, so as a summary, we have that this is a method, a reaction method, or reactive method, that depending on the location, we just compute the forces at every time step, and depending on our control loop, we just compute the total force and apply the control input. This is the equation that we obtain by computing the total force, and we know that the velocity is equals to the force. If we see, the computation of this equation is pretty simple because it only depends on the number of obstacles. And even if we have many obstacles, the force that the obstacles generate when they are there very far is very low. So we can even reduce the complexity by only studying by checking the obstacles that are close to the robot, so we don't need to have problems with the computation. Some of the advantages of this method is that it is very robust to noise and also to perturbations. Since the robot depends on the location, if it receives a perturbation and dislocates the robot, it will just compute the gradient from the new location, and it will not have problems to obtain that. The downside or the negative part of this method is that we have local minima. If we fall in a local minima, we cannot get out of this with this simple method. For that, there are many techniques and many research in robotics about how to avoid that and how to find a solution for that. And almost all the solution for completeness to find a path, if it exists, or if it doesn't exist, we should say that there is no any path. And the solution for this case is just explore the configuration space. We explore the configuration space is a very tedious and hard task, but there are some heuristics that can help with this process. There are sample-based methods that can improve this search. Okay. I am glad you reached this point. If you want to play with the simulations and the potential functions, the Python code in Jupyter will be available in GitHub, and I will place the link in the description. For the next steps, we will study how to localize the robot in the configuration space and how to create a map of the environment. See you in the next session.